This is lesson 8.6, the counting principle. In this section you will solve simple counting problems, use the fundamental counting principle to solve more complicated counting problems, use permutations to solve counting problems, use combinations to solve counting problems. Let's get started here. Simple counting problems. How many puppies are there? This is not a real question. I just like puppies. Okay, simple counting. As you may figure it out, nothing in this class is quite that simple. So let's get started here. There are 8 pieces of paper in a hat. The papers are numbered from 1 to 8. One piece of paper is drawn from the hat and the numbers written down. The paper is replaced in the hat and this is repeated. The two numbers are added together. In how many ways can a sum of 12 be obtained? Think about this for a second and see if you can come up with an answer. In this particular lesson, I'm hoping that you can develop some common sense, and the only way you can develop that is to attempt these problems. Common sense is easily built, but it does not come for free. So unless you actually attempt to do some of these, you're not going to get much out of this lesson. Okay, it might take you a good 5-10 minutes to figure this out, so you may have to pause it. Alright, I hope you've made an attempt. So what happens if you draw, let's say, a piece of paper with a number 1 on it? Well, we're trying to make a sum of 12, so that's no good. What's the next smallest number you can draw from the hat? A 2. Can you make 12 with a 2 if the numbers are papers are numbered from 1 to 8? Nope, that one won't work either. How about the next smallest number? 3. That's still too small because the largest number in the hat is an 8, so that will only make 11. So you need at least a 4. And if you draw a 4 out of the hat, and you write that down, and you put it back, what number will you have to draw next to make 12? You have to draw an 8. So that's one way. So how many other ways can you make 12? Or you can draw a 5 and a 7. That's 2 ways. You draw a 6, put that back, and draw that 6 again. That makes 12. And draw a 7 and a 5. That's 4. Draw an 8. Draw a 4, and that'll be 5 different ways that you can get the sum of 12 by picking 2 pieces of paper out of the hat. Okay, I hope that's understandable. Alright, let's try the next one. Does this problem look different to you? There are 8 pieces of paper in a hat. The papers are numbered 1 to 8. 2 papers are drawn from the hat, and the numbers are written down. The 2 numbers are added together. In how many ways can the sum of 12 be obtained? Well, this is actually a different problem because you're drawing 2 pieces of paper, whereas the last problem, we drew 1 piece of paper, wrote that number down, and put it back, and drew a second number. So how many ways do you think this could be done? Let's see, we would have the same ways of making 12 as last time, so that's 5. The only difference is you're drawing 2 pieces of paper out at a time, which makes drawing 2 6s impossible. So you only have 4 ways that you can make 12. Alright, this is the fundamental theorem of counting. Okay. The fundamental theorem counting just says the number of ways to make multiple events is the product of the ways of each event. Okay, this is a very basic theorem of counting, and you should know this. Let's say Karen bought 3 tops at the mall, and she also bought 2 skirts. How many outfits are there? Okay, she could wear each one of the tops with each one of the skirts, which makes 6 outfits. So the fundamental theorem of counting just says there are 6 outfits because it's 3 times 2. You take the individual events and you multiply them. There's 3 different tops, 2 different skirts. 3 times 2 is 6 different outfits. And that's what we'll be using most of the time in this section on the counting principle. Okay, simple counting. How many area codes are possible? A 3-digit area code. Well, you can have, let's say our area code here is 626. And how many other area codes are possible, or how many total area codes are possible? Well, you can have 1 of 10 digits in the first position, and 1 of 10 digits in the second position, 1 of 10 digits in the third position. This is not including any exclusions. And of course, there are exclusions. For instance, you cannot use a 0 or 1 in the first position, otherwise the telephone company thinks of that as an instruction. As dialing 0 gets an operator and so on. And dialing a 1 tells it that you're dialing out of the area. So that would not occur here, but in this problem it just says how many are possible, having 3 digits. So you can have 0 through 9, so that's 10, and then 0 through 9 and 0 through 9. That means there are 1,000 different area codes possible. Okay. Alright, on a flight to New York, you are asked to place an order for lunch. You can choose an entree of beef, chicken, or vegetarian, a dessert of cake or pie, and a drink of coffee, tea, soda, or water. How many different meals are possible? So you just take the individual events, which is 3, 2 desserts, and 4 drinks. So that will be 3 times 2 times 4, which will give you 24 different possible meals that you can order. Okay. How many 10-digit telephone numbers are possible? Area codes and local numbers cannot begin with a 1 or a 0. So what do you think that answer would be? You probably will need a calculator for most of you, but if you're good with numbers, this is quite simple and you may not need a calculator. Calculator is not needed. Alright, so if you can't use a 1 or a 0, that leaves 2 through 9, so that's 8 possibilities for the first digit, and then for 0 through 9 for the second and third. And then for the local area part, where you don't have to dial the area code, you can't use a 1 or a 0 again, so there's 8 times 10 times 10 times 10 times 10 times 10 times 10. So it'll be 8 times 8 is 64, with 1, 2, 3, 4, 5, 6, 7, 8 zeros behind it. So it's 8 times 8 with 8 zeros behind it. How many 3-letter monograms can be formed, like A, B, and C? So, how many choices do you have for the first position? 26. And how many choices in the second position? 26 and 26. So, since they can repeat, so we'll have 26 times 26 times 26. That gives me 17,576 different monograms that can be formed. A hat contains 26 pieces of paper, each with a different letter of the alphabet. If 3 letters are drawn without replacement, how many 3-letter arrangements can be formed? Well, now this is slightly different because there are letters in the hat and they're not being replaced. So you're going to have 26 different possibilities for the first letter, but then you've already taken one out and you're not putting it back, so now you only have 25 left for the second position and then 24 left for the third position. So you multiply that out, you get 15,600. How many ways can the letters A, B, and C be written? So using only these letters, how many ways can you write them? Well, the counting principle says that you take how many possibilities in the first position. You have 3 letters, so that'll be 3. Once you choose a letter, you can't use that letter for the second position, so you only have 2 letters left to choose from. And then the last one. So if you write them all out, you'll see that you can have A, B, C, A, C, B, B, A, C, B, C, A, and C, A, B, and C, B, A, and that will be all the different ways that you can write them. So there are 6. But like I said earlier, you have 3 different ways to choose the first letter, and then you're stuck with 2 left to choose for the second one, and then you're going to be left over with 1, which you can't choose anything, right? So once you pick the first one, you have 1 less. So what does this look like to you? 3 times 2 times 1? That's just 3 factorial. So if you have 3 letters to choose from, you can just say it's 3 factorial. Or 4 letters would be 4 factorial, because 4 times 3 times 2 times 1. How many different ways can the letters A, B, C be written if the order does not matter? In the last part, that's called a permutation because the order matters. But in this one, if the order doesn't matter, how many ways can you choose between all these 3? Well, you have this thing again. Do you think the answer is the same? If the order doesn't matter? If the order doesn't matter, then these 3 people are the same as these 3 people, and the same as these 3 people, and so on, right? So there's only one way to arrange 3 things if you choose all 3 of them. So it's3C3 is equal to 1, because if you had 3 things to choose from and you have to choose all 3 of them, there's only one way that you can do that. This just means if order does not matter, these are all the same. What is this? We call this a combination lock, but that's actually the wrong name for it because this is really a permutation lock. If it was a combination lock and you had the code was 10, 20, 30, that means you can put those 3 numbers in any order that you want. That would be a combination lock. Because you have to put the combination in the correct order, this makes this a permutation lock. Permutations can be found using this formula right here, where it's NPR, which is like 8 things chosen. Let's see, you have 8 things to choose from, and you pick 3 at a time, so it'll be 8P3. And the denotation is always the total amount goes in the front. That's how many you have to choose from. And then the number that you choose has to be in the back. So the number in the back is always smaller than the number in front. So you never get a negative number here. Okay. So if it was 8P3, then it'll be 8 factorial over 8 minus 3. So it'll be 8 factorial over 5 factorial. All right. So in our previous example, how many ways can this be written? Well, that's just a permutation. So we can use the permutation formula for this, where we have 3P3 means we have 3 things, and we're going to choose all 3 of them. That would be 3 factorial over 3 minus 3, which is 0 factorial, which is 1, which is 3 factorial. That's how we get this. The combination formula, I showed you that yesterday. where you can use the Pascal's triangle or use a calculator, but this is the formula for it. It's the same thing as a permutation, but you have to divide it by how many ways there are to rearrange the items that you have so that you can get rid of all the combinations that are the same. So looking at this, we have 3 factorial over 3 minus 3 factorial, but we have to divide it by the number of ways that we can rearrange these 3 things to make them the same. So that's dividing by 3 factorial again. So that's going to be 1. Simple counting principle for this is how many ways can the letters LOCA be written? So this is one way, right? Or we can say it's 4 factorial, right? Because that's going to be 4 times 3 times 2 times 1. You can choose 1 out of 4 letters to put in the first position, and then you're going to be left with 3 letters left over. Then you can choose 1 out of 3, and then 1 out of 2, and then the last letter is the one that's left over. That's always 1. So that's 4 factorial. So what if you want to know how many distinguishable ways can these letters be written? Distinguishable means that you can tell them apart. Okay, so if I switch this O with that O, I can't tell them apart, so I have to divide that out. So I can, if this was LOCA, if these letters are all different, it'll be 4 factorial. But because we have 2 O's, we have to divide it by 2 factorial. That will eliminate the fact that I switch these two and it looks the same, so I can't count it again. So this will be 4, 3, 2, 1. Cancel the 2 and 1. We get 12 ways that we can have LOCO. And remember, the last one was LOCA, and there's 24. There's half as many because these letters duplicated. What about how many distinguishable ways can the letters banana be written? Well, there's 1, 2, 3, 4, 5, 6. 6 factorial. And there are 3 A's, so you divide it by the ways you can rearrange the 3 A's where you can't tell them apart, which is 3 factorial. And then you also have to divide it by 2 factorial for the 2 N's, where you can switch those and you can't tell those apart. So that means you're going to have 6 times 3, 5 times 4 times 3 factorial over 3 factorial times 2 factorial. And I left that as 3 factorial so I can cancel that factorial. And 2 factorial is 2, and I'm going to cancel that with the 6 or the 4 and get half of 6 or half of 4. You get 3 times 5 times 4, or in my head I do the 4 and the 5 together. That's 20. 20 times 3 is 60. How many distinguishable ways can the letters algebra be written? Well, there's 1, 2, 3, 4, 5, 6, 7 letters. Well, you try and figure this out and see if you can give me an answer. Okay, 1, 2, 3, 4, 5, 6, 7. So it'll be 7 factorial. There's 2 A's divided by 2 factorial. And we can cancel the 2's and we get 2,520 ways. The letters in algebra can be rearranged that are distinguishable. In how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? The order of the 3 letters is not important. So this is a combination one that it is not important. So you're going to use the C formula. So 1, 2, 3, 4, 5 letters, and you're going to select 3 of them. So 5C3 is 10. How many? There are 8 different types of gum at the checkout stand of a store. You decide you want to buy 2 different kinds. How many different ways can you choose 2 kinds of gum? Now, the order, not letters, but the order of the gum is not important, right? If you're going to choose 2, it doesn't matter if you choose one over the other first. Okay, so the order doesn't matter. So this is a combination again. So it's 8C2, which is 28. Just a quick note on randomization or randomness. In order to make some common sense in your head, sometimes we want to put in our own feelings, our own intuition in there, which is going to actually hurt your ability to come up with a common sense. So if you think of a monkey, or letting a monkey choose for you, the monkey has no way of knowing a difference from the letter A, B, or C, so you can either do that, or another way that mathematicians think about them is throwing everything in a hat and you reaching in and pulling out something at random. Understanding versus overthinking. Another problem we have with building common sense in this class is a lot of people or a lot of students overthink the problem. Okay, don't overthink it, but don't just randomly guess. You have to understand the problem, but don't overthink it. So you have to find somewhere in between to figure out it's just right. Now, you have to remember that none of the problems are written to trick you, even though they may seem tricky to you because you don't really understand how to do them that well yet. But they are written well thought out to give you one answer and in the most logical way. And they're trying to, when they're writing the problems, they're trying to eliminate any possibilities of being tricky or being not specific enough. All the problems are trying to say which way is the most specific way we can ask this question to get the answer that we want out of it. So don't overthink the problem. No one's trying to trick you. Okay, this is your Google form. How many different ways can you order a hamburger and a drink if there are 6 different hamburgers and 8 different drinks? Number 2, at We Be Smart University, freshmen need to choose one of 3 classes, one of 3 math classes, one of 6 language art classes, and one of 9 science classes. How many possible ways can a freshman choose his 3 classes? Number 3, how many 7-digit phone numbers are possible if the first digit cannot be a 1 or a 0, and the first 3 digits cannot be a 555, which is reserved for fake numbers used in movies? How many ways can the letters MATH be written if the order is important? Number 5, how many ways can the letters MATH be written if the order is not important? Number 6, how many distinguishable ways can the letters BALL be written if the order is not important? That's it.